Alright, hey y'all, it's Miss Summers. Today is February 7th, 2019. I'm sorry I cannot be with y'all today, but we are still going to do some notes so we don't fall behind. If you are in honors, you should have one or two clean pieces of notebook paper out in front of you. If you are academic, you should just be turned to the next clean sheet of paper in your notebooks. You can approach these notes in one of two ways. One, after I finish explaining these instructions, you can mute it and then just skip through and write everything down and then go back and listen to it. Or you can listen first and then go back and write the important highlights. I want to make sure that you are both able to listen and write, and so that you interact with the information in more than one way. All right, so today's notes is about the movements of Earth through space. We're going to talk about 4 motions as well as how these motions affect life, mainly through creating seasons. All right, so let's start with something that you might be like, what? The Earth does not revolve around the sun, question mark. You know, you might be saying, Miss Summers, you told us that the solar system was heliocentric, and helio means sun, and centric obviously means centered. So what do you mean the Earth doesn't revolve around the sun? What? That's crazy. Well, if we want to be super duper technical, the Earth and the sun orbit this thing called a barycenter between them. A barycenter is a point between two centers of mass. So imagine if you had a like a seesaw, and the fulcrum, that's the thing that the seesaw balances on. If it were in the exact middle, if you wanted to have 2 kids to balance it out, it would have to be 2 kids that are the same size. But if you had a really, really big kid and a really, really small kid, the really, really big kid would have to sit a lot closer to this fulcrum or this point in order to balance out. And that is just like what the barycenter is. The sun is the really, really big kid in this example because the sun is the most massive thing in the solar system. The Earth is really, really super tiny. So as you watch, if you were to watch them orbit, the sun would move just a tiny bit around this little point, and the Earth is making a much larger orbit around that same point. All right, here's a quick video that I want to show you. I'm going to mute my computer. This video is like 3 minutes long. We won't watch all of it. I don't want to play it on TV. There we go. It's gonna load. It's from the Ohio State University, OHIO. Whoop whoop. And we have this person. He's a professor. He's explaining stuff. All right. So here's his meter stick that he's gonna use to show the center of mass. All right. These 2 weights are the same. So the barycenter is exactly halfway between them, so that makes sense for us. But the sun and the Earth are not the exact same. Let's skip ahead and see. So he's going to add, whoops, yep. So as he adds weights, he has a little baby stuffed warthog and a mommy stuffed warthog. The mommy warthog is a lot bigger, just like the sun is. So in order to balance them out, obviously they're not balanced if your barycenter is in the middle. That doesn't make sense. In order to get this to balance, you have to move the barycenter closer to the bigger mass. And we're going to flip through it. There we go. So he is demonstrating barycenter. He's gotten the seesaw to balance out by putting the barycenter near the bigger mass. Yay! We did it. Okay. I'm going to go out of that video and back to here. Sweet. So there are, between any 2 bodies that are orbiting, like the sun and the Earth, or the Earth and the moon, you're going to have a barycenter between them. All right, so the 2 main motions of Earth. We have 2 main motions. Our first one is rotation. Okay, rotation is the spinning of Earth on its axis. An axis is like the invisible imaginary line that goes through the Earth, sort of like a skewer, if you will. One rotation takes about 24 hours. It's a tiny bit less. It's like 23 hours, 56 minutes, and 4 seconds or something like that. It depends on what you're comparing it to, but 24 hours is okay for us. Rotation, write this down and put a big star next to it. Rotation causes night and day. So let's show you how that works, all right? When part of the sun when the part of the earth that is facing the sun, that part is in daylight. On the opposite side, where it's facing away from the sun, is night, all right? So more evidence that the earth is a sphere. Woohoo! So let's take a look. So watch this video. Pretend you're the sun. Let your beautiful sunshiny face is the sun. This is going to go for a minute. Okay, here we are. This is the Atlantic Ocean. So everything you see is currently exposed to sunlight. So West Africa, there's Spain, South America. This side is the east, that side is the west. So because the earth spins this way or rotates this way, the sun appears to rise in the east. All right. There's the Pacific Ocean. Here's Australia. Now you might notice you don't see North America or South America or any of Africa or most of Asia for that matter. This part of the world is in daylight now. The opposite side is in nighttime. So we're going to keep going. This is fun, right? So there's Asia. That's China. That's India. That's Saudi Arabia. Here we are at East Africa. See, Australia went away now. It's on the opposite side. It's now nighttime. There's the entire continent of Africa. There's most of Europe right there. No, I don't want to do that. All right, so that is rotation. Whee! All right, sweet. Our other main motion is revolution. So rotation causes night and day. One revolution is the motion around this barycenter that we just talked about. It is one complete orbit. So one revolution takes 365.25 or 1/4 days. So this is why every 4 years we add an extra day to make up for that 0.25 days. And that's what we call a leap year. Yay! So revolutions make years. Rotations make days and nights, right? So here they are. Here's what they look like together. So here's the sun, the barycenter between the sun and the earth. This is obviously not to scale, but it would be like somewhere like right here. Revolution, we're going around the sun. Rotation, we are spinning. And the moon is revolving around the earth as well. All right, our other two minor motions, which you might not be as familiar with. We have precession and nutation. So precession is a really slow motion where the direction that the Earth's axis is pointing in space changes. So one of these cycles takes 26,000 years approximately. And basically that just changes which way we're facing in space. So right now, our North Star is Polaris. As precession continues in like 13,000 years, I think we're halfway through a cycle right now, our North Star will be Vega. So we are basically like a top as it starts to slow down, it starts to spin, or it starts to sort of change which way it's facing. The other motion is nutation. If you just want to write one word for nutation, put wobble. Wobble. W-O-B-B-L-E. Nutation is this wavy pattern that happens during precession. So basically it changes the tilt of the Earth ever so slightly, like maybe by 1/2 degree or 1 degree at most. It has the tiniest little effect on seasons. So sometimes the Earth is more straight up and down, and the seasons aren't as different. And sometimes it's a little more tilted than normal, and the seasons are a little more extreme. All right, so let's talk. Speaking about seasons, no better time to talk about them. How does our position in space affect seasons? So if you remember from Kepler's laws, and hopefully what you got from yesterday during that assignment that y'all worked on, the distance from the sun doesn't really affect seasons. Because our eccentricity, remember Kepler's first law, and eccentricity is how ovally your orbit is. Because our eccentricity is so very tiny, at aphelion and perihelion, there's not really a huge difference. It's only a few 100,000 miles, which sounds like a lot, but it's really not in the grand scheme of things. Seasons are caused by this tilt. All right, so the Earth doesn't sit straight up and down. The Earth is tilted. Here's the equator, that 0 degrees line of latitude. And it's about 23.5 degrees. All right, nutation is going to change that angle ever so slightly. But 23.5 is mostly what it is. All right, so because the Earth is tilted, different parts, either the northern hemisphere or the southern hemisphere, is either going to get more direct, straight-on sunlight or less direct. And generally, there are fewer seasonal variations at the equator. Somebody asked this earlier in this unit. The equator is always pretty warm because it's usually getting fairly direct sunlight. At the poles, you get very extreme seasonal variations because you're either tilted really, really towards the sun or tilted really, really far. So a good example of this, the midnight sun. If you've never seen this before, it's pretty... No, it's not there! Boo hiss. That's okay. I'll show it to you when I get back. Basically, if you go up to the Arctic Circle or down to the Antarctic Circle, during the summer, you will have 24 hours of sunlight because you're tilted so far towards the sun, even as the Earth rotates, you're still experiencing some sunlight. All right? And likewise, it's the opposite in the winter. During the winter, you have 24 hours of darkness where it's like nighttime all the time, and it looks like the sun's about to rise, but then it goes back down. All right, so here it is. This is in the northern hemisphere, obviously. In June, our sun rays that we're getting, all right, so we have 1, 2, 3, 4, 5 little sun rays here. They are striking a small area. So this means there's more energy that's concentrated, and that's why it gets warmer in the summer. In December, we had the same 1, 2, 3, 4, 5 sun rays, but they're much more scattered. They're over a much bigger area, so the energy's not concentrated, and that's why it gets cooler in the winter. All right, now, right now it's February. We are in the middle of winter right now. We're about to go into spring. Our friends in the southern hemisphere, so here we are in winter. So you can see how the Earth is tilted, how we're up here in North America. Here's the equator, thereabouts. We're tilted away. Our friends down here in the summer, in the southern hemisphere are experiencing their summer. All right, because the Earth is a ball, I cannot stress that enough, the Earth is a sphere, all right? When one half is tilted away, the other half is automatically tilted towards, all right? In a few months, when it's summertime, when it's June, that's when we begin our summer officially, all right? We will be tilted towards the sun, so we'll be getting a bunch of light, and our friends down here in the southern hemisphere will be experiencing their winter. All right. Winter and summer begin on the solstice, which marks either the shortest or longest day of the year. So for us, our winter solstice is in December. That is the shortest day. We get the least amount of sunlight that day. But our friends in the southern hemisphere are experiencing their summer solstice then. In June, in the northern hemisphere, we are going to be experiencing our summer solstice. We will have the longest day of the year. So those are those days where the sun comes up like right around 6 a.m. and it doesn't go, the sun might not set till like maybe, I don't know, like 8:30, 8:45-ish. So we have a lot more light. Equinox, so EQU, that's just like the beginning of equal, happens in either September or March. And it's called equinox because it means equal night, where your day and night are going to be the same length. And that's going to begin summer or spring. Or not summer or spring, excuse me, spring or fall. All right. Autumnal means fall. Vernal means spring. All right. Make sure you have this diagram in your notes. We're going to go over it on Friday. Hopefully I will be able to return by then. But this diagram is going to be super duper important to you. All right. So that is all I have for these notes. If you listen, go back and write and draw pictures. If you wrote things first and then listened, if you need to go back and add anything, please do so. And follow the rest of the lesson outline for today. And I will hopefully see y'all soon.